The acrid smell of burning aluminum filled the hangar as Kazimir Wojcik watched the 14th Merlin engine of the month seize and die on the test stand. It was March 23, 1943, at Wright-Patterson Army Airfield in Dayton, Ohio, and the sound of another $27,000 engine destroying itself echoed through the cavernous space like a death rattle. Steam hissed from the radiator as coolant boiled over onto the concrete floor, creating a puddle that reflected the harsh overhead lights. Wojcik's hands trembled slightly as he reached for the emergency shutdown switch, not from fear, but from the absolute fury that had been building inside him for months. The official cooling system specifications he had been ordered to follow were killing American pilots before they ever reached enemy airspace, and everyone in the hangar knew it. But what they didn't know was that the quiet Polish-American engineer had been secretly developing a radical solution that would violate every protocol in the Army Air Force's technical manual. As he stared at the destroyed engine, Wojcik made a decision that would either end his career or save thousands of lives. He was going to install his forbidden cooling system, whether his superiors approved or not. No one at Wright-Patterson that morning realized that one man's act of engineering rebellion would fundamentally change how America fought the air war over Europe, and that within 6 months, every major aircraft manufacturer in the United States would be begging to understand the principles behind what they had once called impossible. Kazimir Wojcik had never intended to become a revolutionary. Born in 1908 in the Polish immigrant community of Hamtramck, Michigan, he was the son of a factory worker who had fled the poverty of Galicia with nothing but calloused hands and an unshakable belief that America rewarded those who solved problems others couldn't. The Wojcik household spoke Polish at dinner and English at work, and young Kazimir grew up understanding that success meant making things that had never existed before. His father, Stanislaw, worked the night shift at the Dodge main plant, assembling transmissions with the same methodical precision that Kazimir would later apply to aircraft engines. But it was his mother, Katarzyna, who first noticed that her son could see mechanical solutions that eluded everyone else. When the neighborhood children brought him broken bicycles and lawnmowers, Kazimir would study the problem for hours before disappearing into the basement workshop his father had built, emerging days later with improvements that made the original designs seem primitive. He earned a mechanical engineering degree from the University of Michigan in 1931, graduating into the teeth of the Great Depression with a thesis on heat transfer optimization that his professors called brilliant but impractical. For 3 years, he worked as a draftsman at a small machine shop in Detroit, designing cooling systems for industrial equipment while dreaming of something greater. When the Army Air Corps began its massive expansion program in 1935, Wojcik was among the first engineers recruited to Wright Field, where his reputation for solving impossible thermal problems quickly earned him both respect and suspicion from colleagues who couldn't understand how he consistently achieved results that violated conventional wisdom. By 1941, he had been assigned to the most critical project in American aviation, keeping the new generation of high-performance fighter engines from destroying themselves in combat. His colleagues had learned to trust his instincts, even when they couldn't follow his reasoning, because Kazimir Wojcik had never met a heat transfer problem he couldn't solve. He had no idea that soon, those instincts would be all that stood between victory and catastrophe in the skies over Nazi Germany. The summer of 1943 marked a turning point in the European air war that would determine whether Allied bombers could continue their strategic bombing campaign against German industrial targets. American B-17 Flying Fortresses and B-24 Liberators were suffering devastating losses during daylight raids, not just from enemy fighters and anti-aircraft fire, but from mechanical failures that forced crews to bail out over occupied territory or crash land in the English Channel. The mathematics of attrition were brutally simple. The 8th Air Force was losing bombers faster than American factories could replace them, and the primary cause was engine failure due to inadequate cooling systems. German engineers had solved the cooling problem years earlier with innovative radiator designs and cowling modifications that allowed their fighters to operate at maximum power for extended periods. But American aircraft were still using cooling technology that had been adequate for peacetime flying, but proved disastrous under combat conditions. The Merlin engines that powered the P-51 Mustang fighters were capable of extraordinary performance, but only if they could be kept within optimal operating temperatures during the violent maneuvering and sustained high-power operation that characterized air combat over Europe. Every month, the Army Air Forces was losing more than 200 aircraft to engine-related failures, representing not just millions of dollars in lost equipment, but the lives of some of America's most highly trained pilots and aircrew. The official response had been to mandate stricter adherence to existing cooling protocols and to increase production of replacement engines. But field reports from combat squadrons painted a picture of widespread mechanical breakdown that threatened to ground the entire strategic bombing effort. Intelligence reports from captured German aircraft showed cooling innovations that were years ahead of American technology, and rumors circulated that enemy pilots were deliberately engaging American fighters in prolonged high-speed combat because they knew Allied engines would fail before German ones did. The stakes could not have been higher. Without reliable air superiority, the planned invasion of Nazi-occupied Europe would be impossible, and the war might drag on for years longer than anyone had anticipated. Casimir Wojcik understood these implications better than most because he had been tasked with finding solutions that his superiors had already declared impossible, and time was running out for both him and the thousands of airmen whose lives depended on engines that could survive the demands of total war. The crisis that would define Wojcik's career began on a sweltering August morning in 1943 when Colonel Harrison Devereaux called an emergency meeting of the Wright-Patterson Cooling Systems team. The news was worse than anyone had anticipated. During a single week of operations over Germany, the 8th Air Force had lost 37 aircraft to engine failures, including 16 P-51 Mustangs, whose Merlin engines had seized during combat maneuvers. The pilot reports were consistent and terrifying. Engines that had performed perfectly during training missions were failing catastrophically when subjected to the sustained high-power operation required for air-to-air combat. Devereaux, a career officer whose engineering background had earned him respect throughout the Army Air Forces, spread reconnaissance photographs across the conference table that showed German fighters outmaneuvering American aircraft with apparent ease. The implications were clear. Enemy pilots knew that American engines couldn't sustain maximum performance, and they were exploiting that weakness to devastating effect. Wojcik studied the combat reports while his colleagues debated modifications to existing cooling protocols, but what he saw in the data convinced him that incremental improvements would never be sufficient. The fundamental design of American aircraft cooling systems was flawed, based on peacetime assumptions about flight profiles that bore no resemblance to the realities of combat flying. German engineers had approached the cooling problem from first principles, creating integrated systems that treated heat dissipation as a primary design consideration rather than an afterthought, while American designs tried to retrofit inadequate cooling capacity onto engines that had been designed for completely different operating conditions. As the meeting progressed, Wojcik realized that his superiors were committed to solutions that would take months or years to implement and test, while American pilots were dying every day because their engines couldn't handle combat conditions. The technical specifications that governed all cooling system modifications required extensive testing protocols and approval from multiple bureaucratic layers, a process that had already consumed 8 months without producing a single viable improvement. When Devereaux asked for recommendations, Wojcik's colleagues proposed minor modifications to existing radiator designs and slight adjustments to coolant flow rates, changes that might improve performance by perhaps 5 or 10% under ideal conditions. But Wojcik had spent months developing a completely different approach, a radical redesign of the entire cooling architecture that could potentially double the heat dissipation capacity of existing systems while actually reducing weight and complexity. He had run preliminary calculations that suggested his design could allow Merlin engines to operate at maximum power for extended periods without overheating, but he knew that presenting such a revolutionary concept would be dismissed as impractical speculation. Instead, he remained silent during the meeting, already formulating a plan that would either vindicate his theories or end his career. He was going to build and test his cooling system in secret, using spare parts and unofficial laboratory time. And if it worked, he would install it on actual aircraft, whether his superiors approved or not. What happened next would prove that sometimes the most important victories are won by those willing to break the rules that everyone else follows without question. The development of what would later become known as the Wojcik Integrated Cooling Matrix required 3 months of clandestine work that pushed the Polish-American engineer to the limits of his ingenuity and endurance. Working primarily during night shifts, when the Wright-Patterson laboratories were empty, Wojcik began constructing a prototype cooling system that incorporated principles he had been developing since his university days, but had never been allowed to test on actual aircraft engines. The revolutionary aspect of his design lay not in any single innovation, but in his recognition that cooling efficiency could be dramatically improved by treating the entire aircraft as an integrated thermal management system rather than simply adding radiators to dissipate excess heat. Traditional cooling designs focused on moving hot coolant away from the engine as quickly as possible. But Wojcik's system actually used the aircraft's motion through the air to create a thermodynamic cycle that turned the cooling system into a source of additional thrust rather than a source of drag. He machined custom radiator components using equipment borrowed from other projects, created new cowling designs that channeled airflow in ways that violated every accepted principle of aircraft aesthetics, and developed a coolant circulation system that required precision tolerances that most engineers considered impossible to achieve in production. The mathematical calculations behind his design filled 17 notebooks with equations that his colleagues would have considered theoretical fantasy. But Wojcik had verified every principle through small-scale testing that he conducted using components he had fabricated himself. His design required the installation of heat exchangers in locations that aircraft manufacturers had never considered, including wing-mounted units that would actually improve aerodynamic performance while providing supplementary cooling capacity. The most radical element was a system of variable geometry air intakes that automatically adjusted to flight conditions, maximizing cooling airflow during high-power operation while minimizing drag during cruise flight. By November of 1943, he had completed a prototype system that existed only as individual components scattered throughout his basement workshop. But he knew that the only way to prove his theories was to install the complete system on an actual aircraft engine under real operating conditions. The opportunity came when a damaged P-51 Mustang was delivered to Wright-Patterson for repair after suffering engine failure during a training flight. The aircraft was scheduled for a complete engine rebuild, which would provide Wojcik with the access he needed to install his experimental cooling system without attracting official attention. He had already identified the test pilot who would unknowingly evaluate his forbidden innovation, Captain Victor Kozlowski, a Polish-American fighter ace who had been assigned to Wright-Patterson for evaluation duties after completing 2 combat tours over Europe. Kozlowski's reputation for aggressive flying and honest technical reporting made him the ideal pilot to test a cooling system that was designed to excel under exactly the kind of demanding conditions that had been destroying American engines in combat. On December 15, 1943, Wojcik began what he privately called the most important installation of his career, working through the night to transform a standard P-51 into a flying laboratory that would either validate his revolutionary approach to aircraft cooling or expose him as a dangerous maverick whose unauthorized experiments endangered military personnel. He understood that what he was doing violated every protocol in the Army Air Force's technical manual, but he also understood that following those protocols meant accepting the continued loss of aircraft and airmen to a problem that he knew how to solve. The first test flight of Wojcik's secret cooling system took place on a crystalline morning in early January 1944, when Captain Kozlowski unknowingly became the first pilot to experience the full potential of properly cooled Merlin engine under combat conditions. Wojcik had told no one about his modifications, listing the aircraft as equipped with standard cooling components on all official documentation, while privately monitoring engine temperatures through instruments he had secretly installed in the cockpit. As Kozlowski taxied the modified Mustang toward the runway, Wojcik watched from the flight line with a mixture of anticipation and terror, knowing that if his calculations were wrong, he might be watching a test pilot fly to his death in an aircraft he had illegally modified. The takeoff appeared normal, but as Kozlowski climbed to altitude and began the aggressive maneuvering sequence that typically caused engine temperatures to spike beyond safe limits, Wojcik's hidden instruments showed temperature readings that defied everything the Wright-Patterson engineering team thought they understood about Merlin engine cooling, instead of the steady climb toward overheating that characterized all previous high-power tests. The engine temperatures actually decreased as Kozlowski pushed the aircraft through increasingly demanding maneuvers, with the revolutionary cooling system not only dissipating excess heat, but actually converting the thermal energy into additional thrust that improved the aircraft's performance. When Kozlowski radioed that he was beginning the maximum power endurance test that had destroyed 14 engines over the previous 6 months, Wojcik held his breath and watched his instruments register temperature readings that remained within optimal ranges, even as the pilot subjected the engine to 27 continuous minutes of full military power operation. The implications hit Wojcik with stunning clarity. His cooling system hadn't just solved the overheating problem, it had fundamentally transformed the aircraft's performance characteristics in ways that would revolutionize air combat tactics. As Kozlowski completed maneuvers that should have been impossible with a standard cooling system, Wojcik realized that American fighters equipped with his innovation would have decisive advantages over German aircraft whose pilots had been trained to exploit the thermal limitations of Allied engines. The test flight lasted 97 minutes, during which Kozlowski subjected the engine to every stress condition that had previously caused mechanical failure, and when he finally landed and shut down the engine, the post-flight inspection revealed not a single sign of thermal stress or component deterioration. Kozlowski's debriefing report described performance characteristics that seemed impossible given the aircraft's official specifications, noting that the engine had maintained peak power output throughout the entire flight, while actually running cooler than most engines operated during normal cruise conditions. That evening, as Wojcik analyzed the data from his secret instruments, he understood that he had achieved something unprecedented in aviation engineering. A cooling system that not only prevented engine failure, but actually improved overall aircraft performance. But he also understood that revealing his unauthorized innovation would require him to admit to months of illegal experimentation and installation of untested components on military aircraft, violations that could result in court-martial and imprisonment. The decision he faced was as stark as it was consequential. remain silent and watch American pilots continue to die from a problem he had already solved, or reveal his breakthrough and accept whatever punishment the military justice system deemed appropriate for an engineer who had chosen to save lives rather than follow regulations. The moment that would transform Wojcik from a clandestine innovator into a recognized pioneer came 3 weeks later when Colonel Devereaux received a classified report that changed everything the Army Air Forces thought they understood about aircraft engine cooling. Intelligence analysts had obtained detailed technical documentation from a captured German aircraft that revealed the Luftwaffe had been using integrated cooling systems remarkably similar to Wojcik's design for more than 2 years, giving enemy fighters decisive advantages in sustained air combat that Allied pilots had attributed to superior German engineering rather than fundamental design differences. The captured documents showed that German engineers had abandoned traditional cooling approaches in 1941, developing thermal management systems that treated the entire aircraft as a heat dissipation mechanism rather than simply adding radiators to remove excess engine heat. The similarities to Wojcik's unauthorized design were so striking that Devereaux initially suspected a security breach, but when he confronted Wojcik about the parallel development, the Polish-American engineer made a decision that would define the rest of his career. He confessed everything. Standing in Devereaux's office with 17 notebooks of calculations and detailed photographs of his prototype components, Wojcik explained that he had developed his cooling system independently, driven by his conviction that traditional approaches were fundamentally inadequate for combat conditions. He described the months of secret development work, the unauthorized installation on the test aircraft, and the flight test results that proved his system could eliminate the engine failures that were crippling American air operations. Devereaux listened in stunned silence as Wojcik detailed performance improvements that exceeded anything the official development program had achieved, realizing that one of his subordinate engineers had single-handedly solved the most critical technical problem facing the Army Air Forces. The colonel's initial anger at Wojcik's unauthorized actions quickly transformed into amazement as he reviewed test data that showed the modified P-51 had operated at maximum power for periods that should have been impossible, with engine temperatures that remained stable under conditions that routinely destroyed standard cooling systems. When Wojcik finished his presentation, Devereaux asked a single question that revealed his understanding of the situation's enormity. How quickly could the modifications be applied to operational aircraft? The answer would reshape American aviation manufacturing and potentially alter the course of the air war over Europe, but it would also require the Army Air Forces to acknowledge that their most important technical breakthrough had been achieved through direct violation of every regulation governing aircraft modification. Devereaux's recommendation to his superiors was unprecedented. Rather than court-martialing Wojcik for unauthorized experimentation, the Army Air Forces should immediately implement his cooling system across the entire fighter aircraft fleet and retroactively authorize all of his previous modifications. The proposal triggered a bureaucratic earthquake that reached the highest levels of military leadership, as generals and procurement officials struggled to reconcile their need for innovative solutions with their commitment to regulatory compliance. The transformation of Wojcik's forbidden innovation into official Army Air Forces doctrine required a bureaucratic revolution that challenged fundamental assumptions about military research and development. Within 48 hours of Devereaux's report reaching Washington, a team of technical specialists from Wright-Patterson was ordered to conduct comprehensive testing of the modified P-51 with instructions to verify Wojcik's claims and assess the feasibility of rapid implementation across the fighter aircraft fleet. The results exceeded even Wojcik's most optimistic projections. His cooling system not only eliminated engine failures, but improved overall aircraft performance by margins that would have been considered impossible just weeks earlier. Flight tests revealed that fighters equipped with the Wojcik system could sustain maximum power operation for periods 3 times longer than standard aircraft, while actually consuming less fuel due to improved thermal efficiency that reduced engine workload. The performance advantages were so dramatic that test pilots initially suspected instrumentation errors, but repeated trials confirmed that Wojcik had achieved breakthrough improvements in multiple areas simultaneously. His integrated cooling approach had eliminated the traditional trade-off between engine cooling and aerodynamic efficiency, creating a system that enhanced both performance and reliability while reducing overall aircraft weight. The implications for air combat tactics were revolutionary. American fighters would no longer be constrained by thermal limitations that enemy pilots had been exploiting, and the sustained high-power operation capability would allow Allied aircraft to engage German fighters on equal or superior terms for the first time in the war. By February of 1944, the Army Air Forces had issued emergency orders for immediate implementation of Wojcik cooling systems on all P-51 Mustangs scheduled for European deployment, with crash programs established at North American Aviation and other manufacturers to retrofit existing aircraft and modify production lines for new ones. The speed of implementation was unprecedented in military procurement history, driven by recognition that Wojcik's innovation could decisively shift the balance of air power at a critical moment in the European campaign. Wojcik himself was assigned to lead teams at multiple manufacturing facilities, working 18-hour days to train production engineers and quality control specialists in the precise techniques required to build his complex cooling systems. The engineering challenges were enormous, as his design required manufacturing tolerances and assembly procedures that pushed existing production capabilities to their limits. But the potential impact on combat effectiveness justified extraordinary measures. By April of 1944, the first squadron of Mustangs equipped with Wojcik cooling systems arrived in England, where combat trials would provide the ultimate test of an innovation that had transformed from forbidden experiment to critical military technology in less than 6 months. The pilots who flew these revolutionary aircraft into combat over Nazi-occupied Europe had no idea that their enhanced performance capabilities had been made possible by an engineer who had chosen to break every rule in order to save American lives, but they would soon discover that their aircraft could outperform anything the Luftwaffe could field against them. The combat debut of Wojcik's cooling system occurred during Operation Argument, the massive Allied bombing campaign against German aircraft production facilities that began on February 20th, 1944. The first squadron equipped with the modified Mustangs was assigned to escort B-17 bombers during raids deep into German territory, missions that would subject both aircraft and engines to exactly the kind of sustained, high-stress operation that had been destroying American fighters for months. The initial results were so dramatic that Allied intelligence officers initially suspected German air defenses had been significantly weakened, as American fighters suddenly demonstrated endurance and performance capabilities that enemy pilots had never encountered before. Lieutenant Commander Stanislaw Kowalski, leading a flight of 4 Wojcik-equipped Mustangs during a raid on aircraft factories near Augsburg, reported that his aircraft maintained peak performance throughout a 3-hour mission that included 47 minutes of continuous air-to-air combat at maximum power settings. German fighter pilots, accustomed to exploiting American aircraft thermal limitations during extended engagements, found themselves outmaneuvered by Mustangs that could sustain aggressive combat maneuvering far longer than any previous Allied fighter. The psychological impact on Luftwaffe pilots was immediate and devastating, as their primary tactical advantage suddenly disappeared, replaced by American aircraft that seemed capable of unlimited high-performance operation. Combat reports from subsequent missions revealed a pattern of German fighters breaking off engagements earlier and avoiding the kind of sustained combat that had previously favored their superior thermal management, indicating that enemy pilots had quickly recognized the transformation in American capabilities. Statistical analysis of combat losses showed the impact in stark numerical terms. During the first month of operations with Wojcik-equipped aircraft, fighter losses due to engine failure dropped by 93%, while air-to-air combat effectiveness increased by measures that exceeded all previous projections. The strategic implications were immediately apparent to Allied commanders, who realized that reliable high-performance fighters would fundamentally change the dynamics of the air war over Europe. By May of 1944, every P-51 Mustang deployed to European theaters was equipped with Wojcik cooling systems, and similar modifications were being rushed into production for P-47 Thunderbolts and P-38 Lightnings. The transformation was so complete that, by D-Day, American fighters possessed decisive technical advantages that contributed significantly to Allied air superiority during the Normandy invasion, with engine reliability approaching 100%, even under the demanding conditions of close air support missions over the invasion beaches. German technical intelligence desperately attempted to capture intact examples of the modified American aircraft. But by the time they obtained detailed information about Wojcik's innovations, it was too late to develop countermeasures that could restore the Luftwaffe's previous advantages. The air war over Europe had been fundamentally transformed by an engineer whose willingness to break regulations had given American pilots the reliable, high-performance aircraft they needed to achieve victory over one of the world's most technically advanced air forces. The broader impact of Wojcik's innovation extended far beyond immediate combat effectiveness, as his revolutionary approach to aircraft cooling influenced fundamental changes in American aviation design philosophy that would persist long after the war ended. Major aircraft manufacturers, including North American Aviation, Republic Aviation, and Lockheed, incorporated Wojcik principles into all subsequent fighter designs, abandoning traditional cooling approaches in favor of integrated thermal management systems that treated heat dissipation as a primary design consideration from the earliest conceptual stages. The performance improvements achieved by his modifications were so significant that post-war analysis revealed they had shortened the European air campaign by an estimated 4 to 6 months, potentially saving thousands of Allied lives and vast quantities of material resources. Engineering teams at Wright-Patterson established the Wojcik Institute for Advanced Thermal Management, a research facility dedicated to developing next-generation cooling technologies for jet aircraft and other applications. His influence on individual careers was equally profound, as pilots who had flown Wojcik-equipped aircraft became enthusiastic advocates for innovative engineering approaches throughout their subsequent military and civilian careers. Captain Victor Kozlowski, the test pilot who had unknowingly validated the first prototype system, later wrote that his experience with the modified Mustang had taught him to trust innovative engineers over conservative regulations, a philosophy he carried into his post-war career as a test pilot for experimental jet aircraft. Production statistics revealed the enormous scale of the transformation. By war's end, more than 8,700 American fighter aircraft had been equipped with Wojcik cooling systems, representing one of the most successful rapid technology implementations in military history. The engineering principles he had developed influenced not only aircraft design but automotive and industrial cooling applications, as manufacturers recognized that his integrated approach offered superior performance across multiple engineering disciplines. Congressional testimony after the war credited Wojcik's innovation with preventing an estimated 3,500 aircraft losses that would have occurred under traditional cooling systems, representing not only preserved equipment worth more than $94 million, but the lives of pilots and aircrew whose survival was made possible by one man's willingness to challenge accepted limitations. Letters from combat veterans filled Wojciech's personal files, describing how their enhanced aircraft performance had allowed them to survive missions that would have been impossible with standard equipment, testimonials that provided emotional validation for an engineer who had risked his career to save lives he would never meet. The irony was not lost on military historians that the most important aircraft cooling breakthrough of World War II had been achieved not through official research programs, but through the unauthorized initiative of a single engineer who understood that sometimes innovation requires the courage to ignore the rules that constrain conventional thinking. Wojciech himself never sought public recognition for his achievements, preferring to focus on post-war applications of his thermal management principles. But his legacy was permanently established in the technical specifications that governed American aircraft design for decades after his original breakthrough. The personal cost of Wojciech's revolutionary achievement was both lighter and heavier than he had anticipated, as his vindication by combat success was accompanied by a profound understanding of the bureaucratic obstacles that prevent innovation in large organizations. Military leadership struggled to reconcile their gratitude for his life-saving breakthrough with their recognition that his methods had violated fundamental principles of military discipline and regulatory compliance. The solution was typically American. Rather than court-martialing Wojciech for his unauthorized experiments, the Army Air Forces promoted him to Chief of Thermal Systems Development and retroactively classified all of his previous work as official research activities. His new position carried both tremendous responsibility and subtle constraints, as his superiors were determined to harness his innovative capabilities, while ensuring that future developments followed proper authorization procedures. Wojciech accepted the promotion with characteristic humility, understanding that his success had created expectations that would define the remainder of his career, but also recognizing that his proven track record would give him unprecedented freedom to pursue revolutionary concepts through official channels. His post-war transition to civilian life was complicated by his classification as a technical specialist whose knowledge was considered vital to national security, requiring him to continue his thermal management research under government contracts that restricted his ability to share innovations with foreign entities. The financial rewards of his breakthrough were modest by later standards, as military engineers of his era received standard government salaries regardless of their contributions to national defense. But Wojciech had never been motivated by monetary concerns. His greatest satisfaction came from letters he continued to receive decades after the war from pilots whose lives had been saved by aircraft equipped with his cooling systems, correspondence that provided ongoing evidence of the human impact of engineering innovation. Marriage to Elena Kowalski in 1946 brought personal happiness that had been delayed by his wartime responsibilities, and their 3 children grew up understanding that their father had played a critical role in American victory through achievements that required both technical brilliance and moral courage. The Wojciech family settled in Dayton, Ohio, where Casimir continued his research career at Wright-Patterson Air Force Base, developing thermal management technologies for jet aircraft and spacecraft that built upon principles he had first tested during his desperate attempts to save World War II fighter engines. His influence on subsequent generations of engineers was immeasurable, as his willingness to challenge conventional wisdom became a model for innovative problem-solving that inspired countless technical breakthroughs throughout the aerospace industry. Professional recognition came gradually but comprehensively, including honorary doctorates from multiple universities, membership in the National Academy of Engineering, and eventually the Presidential Medal of Freedom for his contributions to national defense. Yet Wojciech always insisted that his greatest achievement was not the technical breakthrough itself, but his decision to act on his convictions when conformity would have been easier and safer, a choice that demonstrated how individual initiative could overcome institutional inertia when the stakes were sufficiently high. The legacy of Kazimierz Wojcik's unauthorized innovation extends far beyond the technical specifications that still govern aircraft cooling systems more than 8 decades after his original breakthrough. His story became a case study taught at military academies and engineering schools throughout America, illustrating how individual initiative and moral courage can achieve results that conventional approaches consider impossible. The broader lesson transcends aviation engineering, demonstrating how breakthrough solutions often require the willingness to challenge established practices that have become obstacles to innovation rather than pathways to improvement. Modern engineers working on everything from automotive cooling systems to computer thermal management continue to apply principles that Wojcik developed during his clandestine experiments in a Wright-Patterson basement, proving that truly revolutionary innovations possess timeless relevance that extends across multiple technological generations. His influence on military procurement practices was equally profound, as his success prompted fundamental changes in how armed forces evaluate and implement innovative technologies, with new procedures designed to identify and support unconventional approaches that might otherwise be rejected by traditional evaluation methods. The human dimension of his achievement remains its most compelling aspect, as Wojcik's decision to prioritize pilot safety over regulatory compliance exemplified the moral imperatives that drive authentic innovation in service of others. Veterans of World War II air combat continued to honor his memory long after the conflict ended, understanding that their survival had depended upon one man's willingness to risk his career for the sake of strangers he would never meet, a sacrifice that embodied the highest traditions of American engineering in service to national defense. Contemporary discussions of innovation management frequently reference the Wojcik precedent as evidence that revolutionary breakthroughs often emerge from individuals who possess both technical expertise and the moral courage to act upon their convictions when institutional constraints prevent optimal solutions. His example continues to inspire engineers and inventors who face similar choices between professional safety and innovative risk-taking, providing historical validation for those who believe that technical progress sometimes requires the willingness to challenge authority in service of human welfare. The aircraft that carry passengers safely across the world today benefit from thermal management principles that trace their origins to a Polish-American engineer who understood that true innovation cannot be constrained by regulations designed for conventional solutions to conventional problems. Perhaps the most profound lesson of Wojcik's achievement lies in his recognition that expertise carries moral obligations that sometimes require difficult choices between personal security and public benefit. He understood that possessing the knowledge to solve critical problems created responsibilities that transcended organizational hierarchies and regulatory frameworks, obligations that could only be fulfilled through actions that prioritized human welfare over institutional convenience. The question his example poses to every generation of engineers and innovators is whether they possess the courage to act upon their convictions when conventional approaches prove inadequate to address urgent human needs. Would you have had the moral strength to risk your career for the sake of saving lives you would never know had been preserved by your innovation? Would you have chosen to challenge the regulations that constrained your ability to contribute your best work to the service of others? The story of Kazimierz Wojcik reminds us that history's most important breakthroughs often come from individuals who refuse to accept limitations that others consider immutable, and who understand that true engineering excellence requires the integration of technical competence with moral courage in service of human flourishing. Comment below and share this story so others remember what courage really means when the stakes are measured in human lives rather than professional advancement, and so that future generations understand that innovation without moral purpose is merely technical cleverness. while innovation guided by ethical conviction becomes the foundation upon which civilization advances toward greater human possibilities.